Hey guys, welcome back to my channel. So today we will discuss about composite function. So the name composite, it means made up of several parts or elements. So the composite function, it is a kind of function, but it is made up of maybe two or more than functions. So let's start with the definition of composite function. The definition is if we have two functions f and g such that f is a function from a to b and another function z goes from b to c. Then their composite function denoted by z naught f is defined as z naught f of x of any element of this function goes from a to c. The composite function goes from a to c whenever f is a function from a to b and z is a function from b to c, and z naught of f of x equal z of fx. Composite function of an element is equal to z of the first function, g of fx, for all x belongs to the domain of this first function f. Here we have seen that the domain of a composite function, here domain of z naught f equal domain of f. The domain of this function, composite function of f and z, will be the domain of a. So here this is the definition. Whenever we take two functions f and z, f goes from a to b and z goes from b to c, then their composite functions z naught f is defined as this function goes to a to c and we have an element z naught f of x equal z of as a whole fx for all element x belongs to a. And domain of this composite function is nothing but the domain of the first function f. So basically, how this z naught f equal to z of fx comes. So I will want to show here with figure. If a function goes from a to b, suppose this is the set a and this is b, like that. This is function f. The elements in a are in the form suppose x. Then the image of this element will be f of x, which belongs to the set b. Now another function goes from b to c. Suppose there is another set c and the function b to c is, we take z. Now if this is the element in the set b, in the domain set b, then the image of this fx will be in the form z of fx, right? When we take a function f from a to b, the element in the set a is x then the image of this element x will be f of x, no doubt. Now another function goes from b to c. Then if we take this element as a domain set, then this element will have an image in the form g of fx. So this is called composite of these two functions f and g, which is denoted by, which is nothing but g naught of f of x. So here comes the definition. When we take two functions f and g, f goes from a to b and c goes from b to c, then the composite function of f and g will go from a to c. Composite function will go from a to c. And this composite function will have a domain nothing but equal to the domain of this f, which is a. So this is done. Now we will show with some examples. So the example is, let us take two functions f and g such that f is the function belonging to the elements 1, -1, 4, -2, 9, -3, and 16, 4. And another function g belongs to the last element 4, 8, 3, b2 functions. We need to find the composite function of this f and g. We need to find g naught f. Yes, and yes, there is an important thing. There is an important thing. If there are two functions f and g, if there are two functions f and g, then the composite function g naught f, then the composite function g naught f, the composite function g naught f will exist when range of f is subset of domain of C. Then only we can get the g naught f is existing. Similarly, the composite function f naught g. This is also a composite function of these two functions f and g, denoted by g naught f. But there is another composite function f naught g exists if range of g is subset of domain of f. So here two functions are given f and g. We need to check whether in this case we get g naught f existing or not. Similarly, whenever f naught g will exist or not. So to check if g naught f exists or f naught g exists, in this case we need to follow these two steps. There I will show. Here the domain of f equal, domain is nothing but the set of first elements in the function, right? So domain of f will be set of these elements 1, 4, 9 and 16. 1, 4, 9 and 16. And range of f will be the set of second elements -1, -2, -3 and 4. Similarly, domain of Z is -1, -2, -3 and 4, and range of Z is set of elements -2, -4, -6 and 8. We need to check whether F naught Z exists or Z naught F exists. To check whether Z naught F exists, we need to find range of F is a subset of domain of Z. Here, the range is this -1, -2, -3 and 4. Range of F should be the subset of domain of Z. Now domain of Z what? -1, -2, -3, 4. Here we can see this set is equal to this set. That means we can say this is the subset of this Z. Since range of F, since range of F is subset of domain of Z, therefore we get composite function G naught F exists. Right? I hope you are understanding this. This is the key point. Whenever range of F is subset of domain of Z, we get G naught F exists. That means it is a composite function of these two functions F and Z. Now we need to check whether F naught G exists or not. This is domain of Z. Domains of Z. To check. We need to see range of Z, whether it is a subset of domain of F or not. Now, range of Z is the set of elements -2, -4, -6 and 8. But domain of F is nothing but 1, 4, 9, 16. Is this set a subset of this set 1, 4, 9, 16? Can -2, -4, -6, 8 be a subset of 1, 4, 9, 16? You see here, definitely not. This could not be a subset of this set. Since this condition not satisfies, therefore we get F naught G will not exist here. Therefore, F naught G does not exist. So in this whole example, whenever we take two functions f and z, f containing these elements and z containing these elements, we get the composite function g naught f. The composite function g naught f exists, but the composite function f naught g does not exist. So this is the example of a composite function. So here we have done with this example. Now let us take a look on the theorems related to composite function. These theorems are very important. So the first theorem, theorem 1. If we have two functions f and z, if we take two functions f and z and both these functions are 1, 1, then their composite function g naught f is also 1, 1. So this is the first theorem. If f and g are two functions, which are 1, 1, then their composite function g0 f is also 1, 1. So the solution, the proof, we are given f is a 1, 1 function. Let us take two elements x1 and x2 belongs to the set domain set A. Then f of x1 equal f of x2 implies x1 equal to x2. This is very obvious because this is given in this question. F is a 1, 1 function. So image of this element x1 equal to image of another element x2 implies the elements are equal. So we need to check whether this g0 f is 1 or not. Now z0 of f of x1 equal to z0 of f of x2. We suppose two elements x1 and x2. We suppose the two elements x1 and x2 from the domain set this A. Then z0 of f of x1 equal to z0 of f of x2. If we can show that these two elements x1 and x2 are equal, then we can say that this z0 f is 1, 1. So proceeding in a way. Now by definition of composite function, this z0 f of x1 implies z of f of x1. And the right hand side, z0 of f of x2 implies by definition z of f of x2. Now, since the function z from b to c is a 1, 1 function, therefore z of an element equals z of another element will imply f of x1 equal f of x2, right? Because z is also 1, 1. Since z is 1, 1. And also we have done this before. Whenever f of x1 implies f of, whenever we take f of x1 equal f of x2, we get x1 equal x2. And here the result, it is x1 equal x2. So finally what we have taken initially, z0 f of x1 equals z0 f of x2. Finally we got x1 equal x2. If I see this implies x1 equal to x2, that means these two elements are equal, then we can say that this z0 of f is 1, 1. Therefore, the composite function z0 f is a 1, 1 function only when we have given two functions f and g which are 1, 1. So whenever we take two functions which are 1, 1 function, then we get the composite function g0 f is also a 1, 1 function. That's the first theorem. Other two theorems related to this composite function I will discuss in the next session. So what we have learned today are definition of composite function, domain of a composite function, key points about composite function, that means the existing condition of a composite function. Existing condition. And lastly, theorems related to composite function. But today we have discussed only one theorem, the first theorem. There are another two theorems related to this function. So this will be discussed in the next session. So that's all about this video. I hope you are enjoying the class. If you like my video, then please do subscribe to my channel. That's all. Thank you.